If you've ever taken more than a year of chemistry or physics, you'll probably notice a trend in your studies. You're always taught a concept, but never to its entirety. Take our good and familiar friend, the atom. At first, you're taught that the atom makes up everything, that they are the smallest form of matter and are indivisible. Then you go into a higher level of physics or chemistry, and your professor turns around and tells you, psych, these atoms can be divided into smaller parts. You have your positively charged protons, your negatively charged electrons, and your uncharged neutrons. And for a time, that was how you went about perceiving the idea of an atom. Then you go into an even higher level of physics or chemistry, and your professor, once again, turns around and tells you, psych, these subatomic particles can be even further divided into smaller particles called quarks. First of all, if your professor is turning around and yelling at you and saying psych, you might want to change professors. But at this point, you're probably already losing your mind. Every semester, you have previously believed ideas broken down before your very eyes. But after your short existential crisis, you ask yourself, well, what is a quark? Is it a delicious and creamy German cheese? Is it a type of yogurt? Well, yes and yes. But in this context, they are the fundamental building blocks of protons and neutrons. Meaning they do not have a substructure. The idea of the quark was proposed by physicists Gell-Mann and Zweig, but no evidence was available to suggest so until 4 years later, in 1968, at the Stanford Linear Accelerator, where electrons were launched at protons, and these electrons were found to bounce off of tiny particles inside said protons. But if protons were positively charged and electrons are negatively charged, shouldn't they always attract each other and thus not bounce off one another? This gave evidence to the existence of a smaller building block within the proton. Through experimental observation, it was found that quarks were often found in combinations of 3. Well, how would the charge add up to +1 with a proton and 0 with a neutron? Well, your first thought might be, given that you know about the quarks and their upspins and downspins, the upspin quark could have a charge of +1 and the downspin quark could have a charge of -1. And sure, 2 upspin quarks and 1 downspin quark would certainly add up to the +1 charge of the proton. But at no point can any configuration of 3 +1 and -1 charged quarks ever add up to 0. So how do 3 quarks make up a neutron and a proton? Well, quarks have been found to have fractional charges. The up quark has a charge of 2/3, and the down quark has a charge of -1/3. So if you take a look at this proton with its quark charges, you'll find that it still has the charge of +1, and if you take a look at this neutron, you'll see that it still has a charge of 0. Everything adds up. Now let's talk about quark properties, starting with color charge. Well, how can colors have charge? Well, they don't. But consider color as just another property of quarks. See, quarks follow, just like any other subatomic particle, the Pauli exclusion principle, which states that it is impossible for 2 identical fermions, or subatomic particles, to exist in the same place. But we know that in the case of quarks, 2 identical quarks do indeed exist in the same place. So in 1964, Wally Greenberg suggested that each quark had another property called color, which is used to refer to the strong force charge. But anyways, color would come in 3 varieties for the 3 quarks that exist together. Thus, we would need to come up with an idea where the sum of 3 different things cancel each other out. Incidentally, in 1861, physicist Maxwell was working with a photographer, Sutton, and together they discovered that if the colors green, blue, and red combine, they would appear white. Now we compare this with quarks, 1 quark being green, 1 quark being red, and 1 quark being blue. and the color white, meaning no color. Keep in mind, these colors don't have anything to do with the actual visual representations of color. These are just properties of quarks. This idea fixes the problem with the Pauli exclusion principle, though, because this way, no quark in a pair of three are the same, given that they all have different color properties. This way, they are unique and can indeed exist in the same place with each other. Another property of quarks is the weak interaction. So far, we've pretty much just discussed up quarks and down quarks. There are 4 other types of quarks. Strange quarks, which have strangely longer lifetimes. Charm quarks, which charmed the fascination of scientists at the time. And bottom and top quarks, the logical counterparts to the up and down quarks. But through weak interaction, the property responsible for radioactive decay, these higher mass states of quarks would eventually decay to their lower mass counterparts, being the up and down quarks. So the reason the 4 other quarks are so seemingly unremarkable to us is merely because they don't exist long enough and just end up quickly decaying into up and down quarks. So why do we care? So some super duper ridiculously beyond microscopically small particle has been found. What's so cool about that? Well, it's estimated that the quark may have existed during the very first few moments after the Big Bang. Thus, giving further examination to the quark may shed more light on our universe's history and its beginnings. On top of that, it forces us to consider what else could be on the horizon of atomic discovery. The discovery of the quark implies that there is probably still much more for us to learn about atoms. It also suggests that we are likely on the right path in terms of atomic discovery. So whether you know or don't know about the quark may or may not be significant to you. But the quark's role in scientific discovery has implications of astronomical proportions and will probably lead the way to more new scientific discoveries. So the next time you're in a classroom and you hear the whole spiel on how atoms are only made up of indivisible protons, neutrons, and electrons, you can be that, one guy in class that says, "Nuh-uh, the nucleons are actually divisible with intensely high temperatures into quarks with various fractional charges, and each with their own unique color charges, setting each quark different from one another as to not break the Pauli exclusion principle. These quarks actually set an important precedent for scientific discovery, and it would be foolish to neglect teaching students about them." But again, I'm just saying that you can say that. I am not suggesting that you actually say that in class, because I am 100% sure that the professor will hate you for the rest of the semester, and you will likely be marginalized by the rest of your classmates for being that one guy in class. But at the very least, you now have a better and more accurate understanding of the atomic world around you, and you know there's still much more for you to discover in your studies in chemistry.